This video is on methods of proof. As I mentioned in a previous video, creating and proving new theorems is a chief goal of mathematics. In this video, we present a few methods for proving theorems. They are the method of direct proof, proof by contrapositive, and proof by contradiction. So first we discuss direct proof, which is the most commonly used method of proof in mathematics. And we apply it to a statement of the form, if A, then C. So we want to prove that that statement is true. And the idea, just like in our discussion of propositional logic, is to supply some intermediate statements, B1 through Bn, and show first that one can infer B1 from A, and then B2 from A and B1, and so on and so forth until we're able to infer C. So how does such a proof look in practice? So in propositional logic, we had two columns, right? A collection of statements and a collection of reasons. And as we saw in the last video, though, mathematical proofs are usually not written that way. Usually they're written in paragraph form. So how would we do such a thing? Well, let's suppose we're given a statement like this, for all x, if p of x, then q of x. Suppose we want to establish that statement. Well, we probably begin with a sentence like, for x in whatever the domain is, suppose p of x is true. And then our goal is to supply whatever intermediate statements we need in order to be able to infer that q of x is true. So for an example of direct proof, let's prove this statement. So we're going to prove that if a, b, and c are integers with a dividing evenly into b and b dividing evenly into c, then a divides evenly into c. So by the way, this may be the first time that you're seeing this notation a/b. And that notation is not telling us to make a computation. Rather, it's a statement that the number on the left divides evenly into the number on the right. All right, so we're going to prove that if a, b, and c are integers with a dividing evenly into b and b dividing evenly into c, then a divides evenly into c. So, well, how do we begin? Well, let's begin by supposing the given statement that a divides b and b divides c. Well, what does that tell us? So what does it mean for a to divide evenly into b and b to divide evenly into c? Well, it means that there are integers let's say k and n with b being equal to, say, k times a, and c being equal to n times b. So what does that say about c? Well, c then would be n times b, but b is equal to k times a. And now, what does that mean? Well, that means that a divides evenly into c. And that's the end of our proof, right? It's like what we said a little bit earlier. We start by supposing sort of our given statement, and then we want to supply justified intermediate statements that will result in the conclusion that we want to obtain. All right, now you might be thinking that this is not a very profound result. And if you're thinking that, then you're absolutely right. This is not a profound result. However, this example and several of the other examples that we're going to be doing, while not particularly profound, will give us some practice in these proof techniques. So on this slide, we give another example of direct proof. So before we can get to the statement that we would like to prove, we first need a definition. So for integers x and y, we're going to define x triangle y to mean that 3x plus 5y is equal to 7k for some integer k. So what we're saying is that x triangle y means that 3x plus 5y is some integer multiple of 7. So for instance, we have 3 triangle 1 because if you take 3 times 3 plus 5 times 1, you get 14, and 14 is a multiple of 7. However, 3 triangle 2 does not hold because 3 times 3 plus 5 times 2 is 19, and 19 is not a multiple of 7. All right, now on to the statement that we want to prove. So what we want to prove is that if a, b, c, and d are integers, and we have a triangle b and c triangle d, then we also have, or we can infer, that a plus c and triangle b plus d holds. Okay, so we're going to do this by direct proof. So we're going to suppose the given statement and then try to supply some intermediate statements that will allow us to infer the conclusion. Okay, so let's suppose a triangle B and C triangle D. Then usually in cases like this, it's a good idea to just unpack what the notation means. So that means there are integers, n and m, with 3a plus 5b equaling 7n, and 3c plus 5d equaling 7m. So it might be a good idea now to add these two together. So if we add the two equations together, what we're going to get is that 3 times a plus c plus 5 times b plus d is equal to 7 times n plus m. So now we go back and we look at our triangle notation. So two numbers, like say a plus c and b plus d. So a plus c triangle b plus d holds exactly when 3 times a plus c plus 5 times b plus d is some multiple, some integer multiple of 7. And that's indeed what we have here. So we can conclude that A plus C triangle B plus D holds. And that's the end of the proof. Our next method of proof that we'd like to discuss is proof by contrapositive. And to get started with that, I want to remind you of something we learned a week or so ago. That is, if you have the statement, if P then Q, that is logically equivalent to if not Q, then not P. The proof by contrapositive employs that logical equivalence. So if we want to show a statement, if A then C is always true, it's equivalent to show that not C, if not C, then not A is always true. And we're going to do that by supposing not C is true, and then supplying intermediate statements culminating in a conclusion that not A is true. So if we have, for instance, a theorem of the form for all x, if P of x, then Q of x, and we want to start a proof of that, the very first sentence is probably going to be something like, for x in the domain, suppose not Q is true. And then we proceed to give an argument that not P is true. And that will produce a proof by contrapositive. So here we have an example of a statement that we're going to prove using proof by contrapositive. So for integers a and b, we're going to prove that if 5 does not divide evenly into a times b, then 5 does not divide evenly into a, and 5 does not divide evenly into b. So once again, this is not a hugely profound mathematical statement, but it will give us some practice in proof by contrapositive. So it's nice when you're going to use some method of proof other than direct proof to announce that other method. So the very first thing that I might say in my proof is we're going to do proof by contrapositive. And so in this statement, you can think of 5 not dividing evenly into AB as sort of analogous to this statement or predicate P up here. And you can think about this 5 does not divide evenly into A and 5 does not divide evenly into B as the Q here. So we have to begin by assuming not Q. So in this statement, what does not Q mean? Well, let's suppose not Q, which means that 5 divides evenly into A, or 5 divides evenly into B. So you should take a moment now. If you're not quite sure, you should stop and make sure that this supposition that I've made is the negation of Q. So what do we do now? If 5 divides A or 5 divides B, then at least one of those statements has to be true. So if 5 divides A, there is an integer. N, with A being 5 times n. And so that says that AB would be equal to 5 times NB. And so we would conclude that 5 divides AB. Right? 5 divides evenly into A times B because we see that A times B is an integer multiple of 5. Now, what if it's true that 5 does not divide evenly into A, but it does divide evenly into B? Well, then we would produce a similar argument showing that 5 divides evenly into AB. Now, you could repeat this argument where every place we see an A, we replace it with a B and stuff like that. You can do that if you like, or you can just say that similarly, if 5 divides B, then 5 divides evenly into A times B. And we're done, right? Remember that we wanted to conclude that not P is true, right? So not P in this case would be 5 does divide evenly into A times B. So that's our proof by contrapositive. So here we have another example of proof by contrapositive. Now, this example involves the 4-point geometry that we talked about in a previous video. So here we have A and B that are 2 distinct points on a line U. And we're going to prove that if V is any line with U not equal to V, then A is not on V or B is not on V. So we're going to do proof by contradiction, or excuse me, proof by contrapositive. So we're going to announce that. So we remember, for proof by contrapositive, we want to first assume the negation of our conclusion. So there's our conclusion, which we denoted by, I guess, by Q on the previous slide. We want to assume not Q. So we need to figure out what the negation of Q is. So it would be that A is on V and B is on V. Now we know that A and B are both on U as well. So therefore A and B are on both U and V. Now, if you remember the axioms from 4-point geometry, axiom 1, I believe, says that for any 2 distinct points, there's a unique line that both of them are on. So by axiom 1, we then know that U has to equal V. And if you look now, we're finished with the proof, because this statement P, we want to start with not Q and conclude not P. But not P, the negation of this statement would be that U does equal V. And so this is the end of the proof. Okay, the final method of proof that we're discussing in this video is proof by contradiction. So we have a statement A, and we'd like to prove that it's true. And the way that we're going to do this is by assuming that it's false and then providing intermediate statements that will culminate in inferring a statement F that is known to be false. So we would have then established, if not A, then F. But remember, that's equivalent to this tautology, not F implies the negation of not A, which is A. So now F is known to be false, but not F then would be true. So we would have if a true statement, then A being true, and that would force A to be true by modus ponens. Okay? So, I don't know, colloquially what we do for proof by contradiction is we have this statement, we want to show it's true. To do that, we imagine a world where the statement is false and then show that some kind of absurdity must happen, okay? And that allows us to conclude that the statement must have been true to begin with. Okay, so here's our first example. So we have, for integers a and b, we're going to prove that if 3 times a plus 5 times b is 15, then at least one of a and b has to be odd. So whenever we do some type of proof other than direct proof, we announce the type of proof. So we're going to do proof by contradiction. So that's our first statement in the text of the proof. So here we have this conditional statement, if something, then something. We want to assume that that's false to begin with. So let's suppose (3a plus 5b) is equal to 15. And a and b are both even. Okay, so we're going to assume that this conditional statement is false. This entire thing, we're assuming that that's false. And when will that be false? The only way that can be false is when the hypothesis 3a plus 5b equals 15 is true, but the conclusion, one of a or b being odd, is false. Okay? So suppose 3a plus 5b is 15 and that a and b are both even. Then that means that, what does it mean to be even? Well, it means that it's a multiple of 2. So that means that a equals 2n and b equals 2m for some integers m and n. So therefore, if we look at 15, it's 3a plus 5b. And now a is 2n. And b is 2m. And then by arithmetic, we can factor out the 2. So what do we see here? We see that 15 is a multiple of 2. And that is that's a false statement. Right? So that says that that 15 is even. So this is false. Right? We know that 15 is not even. So the original statement must be true. So we finish our slides with a couple of more examples of proof by contradiction. The example on this slide has to do with prime numbers, so maybe the first thing we should do is make sure we know what a prime number is. So an integer n bigger than 1 is said to be composite if there is another integer, k, strictly between 1 and n, where k divides evenly into n. Now, an integer n bigger than 1 is prime if it is not composite. So it's a theorem that we're going to use in our tool bag. So this is a theorem we're going to just take to be true and use it. In our example is this fundamental theorem of arithmetic. So it says that if you take any integer n bigger than 1, it can be written as a product of primes. And in fact, the theorem goes on further to say that the product of primes is actually unique. Okay, now we come to our example. So we want to prove that there are infinitely many prime numbers. Now, unlike the other examples we've done up to this point, this example is important mathematically. The prime numbers are important in the integers because they serve as sort of the multiplicative building blocks of the integers. And so it's important to know a lot about prime numbers. So here, we're going to prove that there are infinitely many of them, which is not an obvious fact, actually, if you think about it. If you think about a very, very large number, for instance, large numbers are more likely to have divisors than smaller numbers. And so you might think reasonably that past a certain point, every number would be composite. But this theorem tells us that there are actually infinitely many prime numbers. So just like before, whenever we do a proof by some method other than direct proof, it's good to announce it. So we're going to do proof by contradiction here. And we're going to suppose the opposite of our statement and try to show that we're able to conclude something absurd. So let's suppose or imagine a world where there are finitely many primes. So we're going to call them, say, P1 up through Pn. And we're going to let n, capital N, be the number that we get by multiplying all of these primes together and then adding 1 to the product. Now, the fundamental theorem of arithmetic is in our tool belt, so we can apply it to this number, capital N. So by this FTA, fundamental theorem of arithmetic, we know that n, capital N, is a product of primes. That is, it's got to be some product of the primes in this list, P1 through Pn. So that means there's got to be at least one of those primes So there's a prime P sub j with P sub j dividing evenly into n. But this P sub j also divides evenly into this product, P1 times Pn, right? So if you put those facts together, that if P sub j divides evenly into n and P sub j divides evenly into this product, then we would know that P sub j divides evenly into 1. But that can't happen because any prime is bigger than 1, so it can't divide evenly into 1. So that's a contradiction. So we conclude that there are infinitely many primes. So here on our final slide, we do another example of a proof by contradiction. So before we can get to the example, we have some preliminary definitions and theorems that we'll be using in the course of the example. So first, we say a number is rational if it's the quotient of two integers. And I want you to note that the integers themselves are rational because if you take an integer like 2, you can write it as a quotient like 2 over 1. Second, a rational number is expressed in lowest terms if we can write r as a over b, where a and b are integers and a and b have no common positive integer divisors other than 1. And we also have these two theorems that are going to be useful for us. So the first is that any rational number can be expressed in lowest terms. It's probably not a surprise. And then we have theorem 2, and there's a typo in theorem 2 that needs to be corrected. So the theorem should say, suppose p is prime, n is greater than 1, being an integer, and let's suppose that p divides evenly into n squared. Then p must also divide evenly into n. So again, we're supposing p divides evenly into n squared, and we're concluding that p divides evenly into n. Okay, now what we want to do is show that the square root of 2 is not a rational number. And like the previous example, this is a rather important mathematical result. It asserts that there are numbers running around that are not rational. And, this is not a 100% obvious fact because if you look at the rational numbers, they are really peppered throughout the number line. And it would be easy to convince yourselves that, well, maybe that's all there is. But here we're going to show that there are numbers running around that are not quotients of integers. So we're going to do this by contradiction, and as we did before, whenever we have a proof that's not by direct method, we're going to announce that it's proof by contradiction, or whatever the other method is. So remember, proof by contradiction means you suppose that the opposite is true. Suppose root 2 is rational. And we want to come up with some kind of contradiction, some sort of absurdity. So if it's rational, then we can write root 2 as a over b. In lowest terms. And here it wouldn't hurt to refer to theorem 1. Right, so we're using theorem 1 there. Then by arithmetic, we have that 2 times b squared is a squared. So that says that a squared is a multiple of 2. And hence 2 divides evenly into a. That is by theorem 2. So since 2 divides evenly into a, we can write a as 2 times n for some integer n. And we'll also write, if we replace a by 2n, then that means that we can write 2 times b squared as a squared, as we did above, but a squared now is 4n squared. So what does this tell us? If we do a little bit of arithmetic here, this tells us that b squared is equal to 2n squared. So 2 divides evenly into b, again by theorem 2. I guess I should say here that we're using the fact that 2 is a prime number. Now, we have arrived at a contradiction, believe it or not. So observe here that we were able to conclude if root of 2 is rational, and we have written it in lowest terms, that 2 must be a divisor of a, and 2 must also be a divisor of b. But remember that we had written root 2, that is the quotient a over b, in lowest terms, right? And remember, lowest terms means that the integers a and b have no common positive integer divisors other than 1. But we have just seen that a and b are both divisible by 2. So this contradicts the fact that this quotient a over b is in lowest terms. And therefore, we can conclude that the square root of 2 is rational. Or the square root of 2 is not rational, rather.